Hello and welcome to another self-study session. Today we're going to be looking at Leetcode number 207 course schedule. So there are a total of num courses that need to be taken, and it's labeled from 0 to num courses minus 1. And so we're given an array of prerequisites where prerequisites of I is equal to the pair of A, B. And that indicates that we must take course B first if we want to take course A. So for example, the pair 0, 1 indicates that to take course 0, we first have to take course 1. So our task is to return true if we can finish all courses. Otherwise, we need to return false. So how do we solve this problem? Well, the Leetcode description in the related topics section sort of gives us an idea of what we need to use to go about handling this sort of problem. But what if we weren't given this list of related topics? What do we do then? Well, my approach is always to draw it out. And so let's say we were given the data set with these particular pairs, we can then derive the following graph and graph table. And so we have 0 to 1, we see we have an edge 0 to 2, and there's 1 to 2, 1 to 2. And if we put this in a table, we have all the courses here in the first column. In the second column, the dependencies or the prerequisites. And so 0 has 2 prerequisites, course 1 and course 2. Course 1 just has 1 prerequisite, and course 2 has none, it's empty. So we know that because there are no edges leaving course 2. Drawing this out alone can tell us how we can go about solving this problem. So if we look at this graph table here, graph map, and we start with course 0, and then we look at its dependencies, we have 1 and 2. And so let's start with the first dependency. If we go over to that course and then look at its dependency, we have course 2. So then we now look at course 2. Now course 2 has no dependencies. So therefore, of course, we can complete course 2. And so that is going to return true. And that true value is also going to be returned true for course 1 because it's just 2, right? And then course 1 returns true, so this is true. And since we've already solved for course 2, that's also true. And all courses return true, so therefore our result is also going to be true. But what about for a different type of graph? Let's say we have just these two courses, course 0 and course 1. Looking at course 0, we look at its dependency. It's only 1. So then we go over to course 1, look at its dependency. But oh, we're back to course 0. We've already visited course 0. And so we notice here a cycle. And so since this is just going to go on and on, then we will obviously return false. But when we solve for this one, what does that sound like? That sounds a lot like DFS, or depth first search. And that's one of the ways we're going to use to solve this problem. So what we're basically looking for with this particular problem is a cycle or no cycle. And formally, it's just known as a directed acyclic graph. And that is just a directed graph with no directed cycles. And that is, it consists of vertices and edges. So the vertices are, these circles here, and edges, the lines or the arrows, also called arcs, with each edge directed from one vertex to the other, such that the following those directions will never form a closed loop. So this first graph here is a DAG, and the second graph here is not a DAG because it has a closed loop. And so more formally, what we're going to use is a topological sort, and that's just graph traversal in which every node V is visited only after all its dependencies are visited. So a topological ordering is possible if and only if the graph has no directed cycles, which we just discussed. And so we're going to solve this using two approaches, DFS and Kahn's algorithm. So we kind of already showed how the DFS algorithm would work earlier, and that is the more natural way of solving this. Once you draw out the graph table, it becomes pretty clear how to solve this, and the steps that we take resembles strongly DFS approach. So let's look at it. And so we pretty much know what DFS is. I'm not going to go through that. But let's go through the steps again. So basically we want to build a table with each vertex, the course, and the respective prerequisite courses, the dependencies. And so for every course, that's going to be like a loop. And for each of its dependencies, another loop, we recursively boil down to the end of the dependencies, which will be our base case. And the base case is any course that has no dependency right here. And so we return true for such a base case. If all courses can return true, the result is true. Otherwise, it means we have encountered a loop. We keep track of loops by storing what we have already visited. So here we're at in the code. And I am going to show you three different methods. This is the first way of solving it. And we're going to clean up this code. I'm going to show you how to clean up this code. So here we have our method, our two parameters. We essentially don't need this line because the constraints in Leetcode mentions it's going to have at least one course, the array of prerequisites. But, you know, it's there. This is the object for the graph. And here we're going to create our graph table. And if it's empty, if it's undefined for the particular post course, because we have here with the prerequisite, and or once we have completed that prerequisite, then we can complete the other course. So it's AB, and here we have the graph. If it's undefined, we set it to new, an empty array. And we do this for the pre as well, because we can have disconnected graphs. So we need to make sure we check for every vertex in the array or data set. And we push our prerequisite to the array. So that's pretty obvious. Or result variable or visited map or object or visited object or memo. So we're going to be using recursion to solve this. And typically with recursion, if you've ever done any sort of recursive method or studied any form of recursion, you would have come across using memoization or some sort of optimization technique. And so that's what this is for. And so here we have our recursive method. And we know usually in recursion, we return what we've stored in memo. This is our base case. So if it's empty, we return true. And here we have, if we've seen the path already, if we've already walked that path, then we are in a loop. And so otherwise, we've not visited that path. We now set it as true. And here we go through every course and look at each of its dependencies. And here we make our recursive call. And once these recursive calls are returned, we store something in memo. And here is our initial or first recursive call. So that's for every vertex. And we need to loop for every vertex once again, because we could have disconnected graphs. And we simply return our result. So if ever we have seen it, we set our result to false and we return. Now this works just fine. And we can just run. Okay, so we've run this, and we can see that for this particular data set, which is an obvious cycle, we expect false, and we actually got a false value. So these are just the string, the data set, what we expect, and the actual return of the call-in B method. So this works just fine. And actually, when I submitted it to Leetcode, we, it got like it seems to fluctuate. So got a memory usage of 54, and so I guess this doesn't really matter that much because it's the same code. Here it's like 266. I guess it depends on the test cases Leetcode is using. But anyhow, I'm going to show you how to make this slightly better in this other approach. So let's set that, and let's use this approach now. And here we've done the same thing. It's the same thing, we're building our graph. However, the difference this time is that whenever we set a visit, we then delete it because we're done checking it. And once we have actually completed that, we just set it as empty because we know that this empty value is our base case for true. And so the reason we do this, we can optimize in this way rather than having this memo, because we're not actually doing anything with these memo values. It's just like a flag. And so we can use this as our flag. Just set it to empty, and therefore that eliminates our need for using an additional memo object. And we're deleting that here as well. So it's just slightly optimized. It's the same approach. And if we run it, we're going to get the same results, but from Leetcode. Here we can see it uses less memory, and on average it's less than 200 milliseconds. So that's just a slightly optimized approach. And we have another method. So I'm not going to run that. We have another method, and this is a lot more optimized. The difference with this, as you can see, this is a lot shorter. Building our graph is a lot shorter. We have used an array instead of an object for the graph. And the reason for that is because our courses are numbers. So an array, in this case, for this particular problem, would give us better efficiency. And so it's exactly the same. except that we are using an array. And we can run this. It's gonna give the same results, so it's not gonna look like, you know, a difference. But in Leetcode we have 56, so it's much faster than what we had before. As you can see, use a lot less memory as well. So if that is important to you, yeah, you might want to consider these strategies based on the data set and so on. Use the appropriate you know, data structure. So yeah. And one thing I want to note about this first approach is this is the natural way of doing things. I mean, as we know, for recursion, we usually have some sort of memo, and we tend to return what we have in memo. And so doing this on a, you know, tight budget of time, you know, we follow the pattern that we already know. And I'm just mentioning this all to say that when we're pinned for time, we do what we know and then we can optimize. And so we are already used to this approach with recursion, and then call in our function, you know, call in our recursive function and then set in that value and so on. And so this is the, I guess, the quote unquote probably most naive way to solve this using DFS, and then we can later optimize our solution. So that's it for the DFS approach, and we're going to talk about the Kahn's algorithm coming up next. Yep. And yeah, so Kahn's algorithm works by choosing vertices in the same order as the eventual topological sort. And so first we find a list of start nodes which have no incoming edges and insert them into a set S or a queue. And at least one such node must exist in a non-empty acyclic graph. And so if we're looking at this graph right here, which I've changed the node values to letters so that we're not confused by the in degree numbers. Yeah, so if we're looking at this particular graph, we'll see that there are no incoming edges to node A. For B, course B, there's one incoming edge from A, and course C, there are two incoming edges from A and from B. And so we need to find a list of start nodes. And so initially, we're gonna have A in the queue as a start node. And so now we're looking at A, so we're gonna pop A from the queue and put it in our result set. Oops, let's see if we can write that. A. And now we're looking at the dependencies for A. So we're looking at B, and the in degree value for B, we're gonna reduce that, it's gonna be 0. And so since it's 0, B is gonna place onto the queue. We're going to look at the in degree value for C, and it's going to be reduced to 1. And so since B is now in the queue, we're going to pop it from the queue, place it in our result, and from B we have C, right? And when we look at C, it has a value of 1. Now it's going to be 0. We're going to put it in the queue. And we're going to pop C from the queue, place it in the result, and we're actually done. So we can see that we've returned all the courses. So in the end, the way to determine if this is good or not is to just compare the num courses length or value with this result length or total. All right. How about now for a non or a graph that has a loop or non-DAG graph? Okay, so we start like usual with the start node would be A again in this case. Let's use a different color. A, and then we're gonna pop A from the queue, add it to our result, and we're gonna look at the dependencies for A, which is C, and we're gonna reduce that to 1. But then C never turns to 0, and so our queue is gonna be empty, and therefore we're going to return this as our result, and our result is not equal to our num courses length or total, and so therefore the graph contains a loop, and therefore we return false. So that is how that works, and we're going to look at the code for Kahn's algorithm. So here we're at in the code for Kahn's algorithm. We have our graph object, our in degrees array of length of num courses, all pre-filled with 0 values, and that's because we're going to later calculate the in degrees for each vertex. And remember, the in degrees are the number of edges coming into a particular vertex or node. And so this loop here just builds a graph as we've done previously with the DFS version. And after that, we have our queue here. This loop now, that looks for the starter node, so any course with an in degree value of 0 is then pushed onto the queue. We have our order array or result set. Now, while the queue has a length, we want to dequeue the first item. So we take the first item out of the queue, we push it onto our order or result set. Then now we want to look at the course. We want to look at the prerequisites for a particular course right here. So we get the prerequisites, then we decrement the in degree value that is for each prerequisite of a particular course. And now if the in degree value ever becomes 0, then we want to push that prerequisite to, or push that course to the queue. Now this continues while the loop has a length. Once the loop is empty, the queue is empty, then we check the length of the order array against the number of courses, and if they are equal, it means that we can complete all courses, and therefore our graph is directed acyclic graph, right? A DAG. And so if we run this, let's try to run this and see. Start debugging, and the same as what we calculated previously with the DFS approach. And yes, so we can see that this solution is a lot more optimized than our previous DFS solutions. And so we've discussed two ways in which we can solve this particular course schedule problem. And we've shown the evolution of the naive approach or slightly naive DFS approach with the memo object. And we have shown how to clean that code up to optimize for based on the problem statement, the input values. We've used arrays for our DFS approach, and we've seen improvement in the memory usage and also the speed or the efficiency. And now we've just discussed Kahn's algorithm. It actually is the faster way of getting things done, and I hope this self-study session was helpful to you. It certainly was helpful to me because I do like to dig into things and figure out how one would have come about a particular problem rather than just getting the algorithm in my face or getting the answer in my face. I do prefer to know what is the natural way of solving it and how can I improve from my natural approach, the natural human way of solving it. And then from there, we improve. And that's what it's really about, right? I'm writing efficient code and code that scales for larger inputs. Yeah, and so anyhow, thank you again for joining me, and I'll see you next time. Take care.